first session in our technical webinar series on the energy transition from Emerson. And for us, it's a pleasure actually to host this first session in collaboration with Calpine. So we'll go through the agenda on the next slide, and you will see. So first of all, my name is Adrien Caudron. I'm the technical sales director for Emerson E&P North America, and I'm going to give you a quick overview about the different solutions and technology we are providing for the geothermal energy and for other renewable energy as well. And with me today, I've got the pleasure also to introduce Craig Hartline. Craig is a senior geophysicist for the Calpine Corporation, and Craig is going to present what he has been doing for the last 10 years using our technology in order to build a complete geothermal analysis and reservoir management model on the geysers. And then we will conclude our session with a question and answer series session with you. So if we can go next slide, please. So I wanted here to give you like a quick overview about what we have been doing at Emerson E&P Software for the last 45 years. So we've got a lot of experience working with hydrocarbon exploration and production. But lately, during the last 15 years, we started to see much more customers coming from different horizons. Some of them were just pure renewable, pure energy, like focusing on renewable. So that's something that has changed, and we are helping to do this transition to energy, to go and to embrace much more renewable energy within the mix of what we are going to see and what is happening right now. So the projections are saying that in 2050, renewables energy is going to provide 2/3 of the energy mix, and that will be split between wind, solar, hydroelectricity, geothermal, and bioenergy. So going into this, what we see here is a different sector of activity where we are already helping as Emerson E&P Software. So we are providing solutions for the mining industry, in particular looking for lithium, cobalt, and graphite that are key components for creating electric batteries and necessary for the electric vehicles. We are also helping on solar and wind farm extension by doing soils investigation and making sure they are compatible with the development of such farms. Another key important topic that we are doing in renewable energy and clean energy is for the radioactive waste disposal. We are helping to build a geoscience model to find the best candidate to build burial site or deposit containers for the disposal, the safe disposal of radioactive waste. And we want to make sure that those sites are going to be undisturbed for the hundreds of thousands of years to come. Energy storage has been also something we have been helping lately. Either some companies, some energy companies are starting to look into that and to develop ways to store hydrogen or to store compressed air in the ground, transforming literally the ground as a battery system. And this is in order to help with mitigating the disruption of energy you can have when you are using just renewable energy such as solar and wind. Another thing we have been doing lately is our customer has also changed their mindset. So what used to be like pure oil and gas company are now calling themselves energy company. And in order to reach their net zero objective, they are looking much more into carbon utilization and storage, CCUS. So here again, we are helping in different ways that could be in finding some container site and some good candidates in order to store carbon dioxide, but it can be also to improve the production activity by injecting CO2 into oil and gas reservoir. And last but not least, and this is what we are talking about today, it's geothermal energy. So geothermal energy is probably one of the source of energy that is checking all the boxes, because this is one of the few that is clean, competitively priced, reliable, so you don't have disruption, you don't have interruption, and scalable, especially with what is coming in terms of enhanced enhanced geothermal system, EGS, enhanced geothermal system, and low temperature system. we can see a way to start scaling geothermal plants outside of the ring of fire. So I will go next slide, please. So on that one, this is a kind of solutions we are providing already for geothermal. So we can go from fluid characterization, understanding all the thermodynamic production, all the thermodynamic behavior we've got during production and the interaction between the ejecting fluids and our geothermal system. We can look for migration paths using a technology called Geological, SKUA, and other tools. We can also do the complete rock property, temperature, field characterization. So understanding again how our rock formations are working and how we can interact with them in order to extract in the most efficient way possible the heat from the ground. Resource assessment, so this is everything what we have been doing as well with SKUA GoCAD. So it's building subsurface architecture model for doing, for instance, fairway play analysis and identifying the best way possible to exploit our geothermal system. Well planning and drilling, this is key as well, because once actually we have a good idea about how we are going to exploit and we've got our plans for doing our geothermal production, we want to make sure we've got the safest possible and the most efficient wells. It's especially key when we are dealing with complex wells, such as closed loop system. Reservoir management, so this is what Craig is going to show us today. This is how we can use our technology to define spatio-temporal relationship between water injection program, production, the ground deformation, and mitigating the induced seismicity. So this is all done with our technology. So I will go through a next slide, please. And that one, I wanted to introduce that as well briefly, because Craig is going to show you what he has been doing on the geysers. And that was basically building the structural and stratigraphical model, so complete subsurface architecture geo model for his system. And what we can do next is actually we can build a geological grid and use that grid in order to populate it with rock and fluid property and export it to a simulation software such as Berkeley. So we have this connection directly with our software with Berkeley TOF2, TOF3 suite, and we can here do all the flow and transport simulation and thermal simulation within this software. So we can export basically any kind of geological or engineering object from SKUA GoCAD to this reservoir simulation software, and we can also do the post and pre-processing using our technology. And with that, I'm concluding my presentation, this overview about the different solutions from Emerson, and I will pass the mic to Craig. So up to you, Craig.
Okay, thank you, Adrien. Hi, I'm Craig Hartline, a senior geophysicist at the Geysers since 2010. I began my career with 19 years at Phillips Petroleum and ConocoPhillips, then transitioned into renewable energy at the Geysers Geothermal Field. I wish to thank Emerson for the opportunity to provide this presentation, particularly Carmen Comas, Adrien Caudron, and Gabi Yellen. The view on the screen is toward the northwest with the Sonoma Unit 3 power plant in the foreground. I'll talk about an introduction, regional geology, 3D structural model building, induced seismicity analysis and mitigation, fault and fracture interpretation with seismicity alignments, 3D well planning and real-time drilling analysis, community outreach, and some extensive acknowledgments. There are many acknowledgments that the presentation's in. I have been the primary user of SKUA GoCAD 3D visualization and model building software at the Geysers, and have benefited from the efforts of experts across the broad degree of specialties while developing the Geysers SKUA GoCAD 3D structural model. The Geysers, located in Northern California and approximately 75 miles north of San Francisco, is the largest producing geothermal field in the world. Calpine Corporation operations at the Geysers span 45 square miles and include 13 geothermal plants, 80 miles of steam production pipelines, 69 miles of water injection pipelines, and 167 of project roads. Calpine produces approximately 725 million watts of electrical power output from about 315 steam production wells with an average wellhead temperature of 359 degrees Fahrenheit and an average steam production of 35,470 pounds per hour per well. Here is a representative view of the California Independent System Operator's monthly metered renewable energy generation. Solar and wind renewable energy are critical in achieving California's ambitious renewable energy goals, and they do have daily and seasonal energy production variability. Geothermal electricity contributes to California's renewable energy portfolio as reliable baseload power. California generates nearly 6 trillion watt hours per year of renewable geothermal energy. Renewable geothermal resource requirements are a high temperature heat source, permeable reservoir rock, reservoir fluid, a low permeability cap rock, and natural or engineered fluid recharge. This is a plate tectonic evolution animation referenced directly below of the change in plate configuration from 200 million years ago to the present. The Geysers Geothermal Field exists within a complex assemblage of late Mesozoic Franciscan rocks representing the ancient Farallon plate subduction complex. The approximate position of California on North America's west coast is shown in this view. Stepping forward to 170 million years ago, we see the opening of the North Atlantic begin. And to 140 million years ago, we see the opening of the South Atlantic begin. Progressing forward, the main thing to note for this presentation is that it is occurring along North America's west coast as the Farallon plate continues to be subducted beneath the North American continent. At 30 million years ago, the spreading center between the Pacific plate and the Farallon plate descended beneath the western edge of the North American plate. A transition from eastward directed subduction to right lateral strike slip faulting resulted, and that will continue on to the present day. Looking a little closer, the North American West Coast plate tectonics. Approximately 30 million years ago, this transition from eastward directed subduction to right lateral strike slip faulting occurred as the spreading center between the Pacific plate and the Farallon plate descended beneath the western edge of the North American plate. Since this transition, the relative motion between the Pacific plate and the North American plate has been increasingly accommodated by the right lateral strike slip motion along the lengthening San Andreas fault zone. Note the increasing separation of the Rivera and Mendocino triple plate junctions at 30, 20, and 10 million years ago, and also the present day. And here's another look at the North American West Coast plate tectonics. And the comments to make here are that the San Andreas fault exists with right lateral strike slip motion south of the Mendocino triple junction, while north of that triple junction, the Cascadia subduction zone exists, where magma is generated in the subduction zone where the dense oceanic plate is pushed beneath the lighter continental plates and volcanism results, along with the resulting volcanoes along California and Oregon and up into Washington. Now let's look at the San Andreas fault system and the resultant stress field. First of all, this Google Earth image shows the U.S. Geological Survey faults. Those with activity within the last 150 years are shown as red. Those within the last 15,000 years are shown as orange. The maximum horizontal principal stress for this area is north 23 degrees east, and the San Andreas fault system is an extensive system of right lateral strike slip faults that accommodate the relative motion between the Pacific plate and the North American plate over a 60 to 180 mile wide zone. The San Andreas fault itself has average relative motions of 24 millimeters per year. Successively smaller slip rates exist for active faults towards the east. The Macama-Rogers Creek fault zone has average relative motion of 9 millimeters per year, while the Bartlett Springs fault zone has average relative motion of 6 millimeters per year. The resultant stress field at the geysers is responsible for northwest to southwest oriented faults and fractures consistent with the San Andreas fault system, and southwest to northeast oriented faults and fractures due to the transtensional forces. A series of views to provide a better understanding of the Geysers Geothermal Field. First, we'll see the field outline, the nearby communities with black labels, the roads with blue labels, and the major inactive fault zones from surface interpretations. These control the development of this now vapor-dominated geothermal resource. Beginning about 1.1 million years ago, a 1400 Fahrenheit multi-phase granite pluton, locally known as the felsite, began intruding the brittle Franciscan greywacke found throughout the subsurface of the geysers region. Extensive fracture enhancement above the granitic pluton occurred due to mechanical and hydraulic forces associated with intrusion, along with contact thermal metamorphism of the overlying greywacke to a hornfelstic greywacke. The containment of the initial hydrothermal reservoir was primarily dependent on the transition from abundant open fractures to very limited open fractures with decreasing depth. This is well represented in the present day North Geysers. The present maximum enthalpy, or 465 Fahrenheit vapor-dominated Geysers geothermal reservoir, exists due to a phreatic eruption approximately 250,000 years ago, the subsequent boil down, and reservoir flushing or dilution from the southeast to the northwest, lowering non-condensable gas and chloride concentrations. Finally, renewed heating by additional magmatic intrusions as recently as 15,000 to 10,000 years ago have resulted in a high temperature zone in the northwest geysers. The extreme surface topography of the geysers causes access limitations, prohibitive costs for active 2D and 3D seismic data acquisition, and also severe datum concerns for any active 2D or 3D seismic data imaging. Additionally, extreme subsurface conditions such as high temperature and corrosive fluids significantly limit the use of typical oil and gas geophysical logging methods to investigate the properties of the geysers' complex metamorphic rocks and fractured steam reservoir. Consequently, the 3D structural model building primary constraints are 940 lithology log segments, along with topologic surfaces, steam entries, ArcGIS surface geologic maps, and seismicity centers. The secondary constraints are also listed. In the upper right, we can see in the map view well quarters SEO2 and SEO3 within the project. These are also seen in cross-sectional view at left in a view that starts from the south and will be rotated around to south 50 degrees east and 5 degrees above the horizontal. Note that this is an area of the field where the correlations are especially good. Much of the field is much more geologically complex. Here we can see in this view from southwest to northeast the surface topography, the lithology markers, and the introduction of the lithologic types and their boundaries. Importantly, this 3D structural model assists with well planning and real-time drilling analysis. In this case, the green curve is a drilled well. Now let's look at the 3D structural model as it's constrained by ArcGIS surface geologic mapping and lithology logs. ArcGIS compiled surface geology is imported as a georeferenced image. This is texture mapped onto the topographic surface. The top felsite granitic intrusion is shown for reference, along with the top serpentinite intersection and the base serpentinite intersection on a USGS and industry-derived geologic map. The top serpentinite is shown as a depth scale color surface. The base serpentinite is shown as surface intersection points. And stitching all of these things together, we can see that the surfaces are created within this limited structural model that encounter the surface. Now let's look at structural model building within the Emerson SKUA GoCAD software at the field level. And here we can see in map view the field outline in lower left, and also see the well slice outlined. And this well slice consists of 271 well segments, 216 of them which have lithology logs. I'll quickly discuss these segments. A segment can be an original hole, a fork, a sidetrack, a deepening. Now, introduced is the top granitic intrusion or felsight that's color scaled by depth down to 6,000 feet subsea, along with the top horn felsic graywacke as a translucent tan surface. The top steam contours are color scaled by depth. The base serpentinites is shown as dark purple. The top serpentinite is light purple. And then the top topographic surface for a limited portion of the surface is shown color scaled by depth. So this is one good look. Now, power generation results in a 75% loss of steam mass to the atmosphere as a yearly average. So we will discuss the Geysers treated effluent recharge project. The Southeast Geysers effluent pipeline has been active since late 1997 and provides 5.2 million gallons per day of treated effluent. The Santa Rosa Geysers recharge project has been active since late 2003 and provides 12.6 million gallons per day of treated effluent. Additional recharge comes from power plant condensate. We recover about 25% of the power plant steam in the condensers, and creek water, which is available during high precipitation periods. Induced seismicity at the geysers occurs as cool recharge water free falls into hot rock and reactivates the fractures through thermal contraction. Modest pressure increases also reactivate fractures. The water flow descends down the borehole under the influence of gravity to the top of the standing water column, moves out into the steam reservoir, and is converted to steam for additional production. Calpine Corporation has well-developed community relations programs and worldwide seismicity research collaborations to address induced seismicity at the geysers. A very good example of this is seismic event information online in real time due to a very valuable collaboration with Lawrence Berkeley National Laboratory and the United States Geological Survey. Recent seismicity trends for the field are very encouraging. Let's discuss the permanent seismic monitoring networks at the geysers. First of all, the Lawrence Berkeley National Laboratory network was installed in 2003 and now consists of 34 three-component stations. Strong motion accelerometers have been installed along the eastern perimeter of the field to monitor shaking experienced by the communities. And the U.S. Geological Survey regional network has 7 stations which contribute to the seismicity hypocenter and magnitude determinations for the geysers' seismicity. The geysers' yearly field-wide steam production and water injection in billions of pounds are referenced to the scale at right. The number of seismic events per year within the specified thresholds are referenced to the scale at left for the years 1960 through 2021, which is the scale at the bottom. The rapid reservoir decline, the red curve, in 1987 results from less than optimal reservoir management by many operators. Basically, there were too many people fishing out of the same pond. The water recharge projects introduced in late 1997 and late 2003 are indicated on the graph. Note that the field is now much closer to mass balance. A steady state reservoir is optimal for sustainable production and for seismicity mitigation. Proper scaling of water injection and seismicity profiles highlight the direct correlation between water injection and induced seismicity through approximately 1995. After that time, seismicity counts generally descend below anticipated levels based on this previous correlation, with the degree of decoupling more pronounced for increasingly higher magnitude thresholds. This is seen at magnitude 2 to 2.5 now, where we can see this decoupling has become more significant after 1995. 2.5 to magnitude 3.0 seismicity, and importantly, for magnitude 3 to 3.5 seismicity, the results are very encouraging for future operations at the geysers and relations with our surrounding communities. And one more view that's very important looks at all magnitude 3 and greater seismicity, and utilizing all of this information, we can see that constructing a trend line to this, that the seismicity of magnitude 3 and greater is descending at about 0.5 events per year. So this is very encouraging for future operations at the geysers. And it should be noted that the U.S. Geological Survey and the California Geological Survey have identified no surface map active faults within the geysers, and the highly fractured steam reservoir, defined by extensive drilling activities and recent induced seismicity pattern analysis, provides confidence there is not sufficient fault area to support what would be considered a large earthquake at the geysers. This animation shows the cumulative water injection as a purple disk with radius scaled to the cumulative volume injected, along with the seismicity occurring for the period January 1980 through December 21. This animation is starting, and comments to be made here are that SKUA GoCAD software was purchased in 2011 by Calpine Corporation with goals of 3D visualization and 3D seismicity analysis for a refined understanding of the spatial and spatiotemporal relationships between water injection and induced seismicity, and also for 3D visualization as an improved communication tool for public outreach and technical discussions. During software utilization for the previously stated goals, it became apparent that the development of the Geysers 3D structural model could benefit steam production and water injection well planning, real-time drilling analysis, induced seismicity analysis mitigation, and assist with reservoir management. This cross-sectional view from the southwest shows the extreme variability in steam reservoir thickness. The cumulative water injection volume, shown as purple discs with radii proportional to the cumulative water injection, are posted at the center of injection, defined by initial steam entry pressure increases. So we can see the significant variability in the reservoir thickness throughout the field, looking from the southwest. Now I'd like to look at a synchronized monthly water injection and induced seismicity animations. We're looking at a yearly interval since 1984 with seismicity from 2,000 to 10,000 feet subsea. The monthly water injection volumes displayed for the month of March in each case are equivalent to the blue disk radius. And these topographic double difference seismicity hypocenters are depth scaled by sphere color, they're magnitude scaled by sphere size, and they're provided by the USGS earthquake catalog. The dates are shown in the lower left, and I'll just begin to progress through this. And the point I want to make is that as the water is injected into the field, the individual wells are not providing a uniform distribution of seismicity away from the wellbore. What we're seeing are significant patterns developing, and they do have significance on interpretation of the subsurface at the geysers. Synchronized time animations with Emerson SKUA GoCAD 3D software have allowed improved understanding of the spatiotemporal relationships between water injection, induced seismicity, and faults and fractures at the geysers. Let's look at some selected seismicity alignments from northwest to southeast, showing alignments that are interpreted on this volume, and also within the yellow areas from southwest to northeast. So these are all important to consider. And now let's look at this in more detail on the next slide. But first, I'll make the comment that these induced seismicity patterns are indicative of permeability variations in fluid flow. The geyser steam reservoir appears to be subdivided by intersecting zones of faulting and fracturing, the majority of which are oriented northwest to southeast and southwest to northeast, which is consistent with the regional stresses. Now, looking at one particular depth slice with north left, we can see that there are patterns that exist within here, or alignments. And if we look at several slices, either in depth or cross-sectional, if we see these patterns represented on adjacent slices, this is something important to consider for the development of fracture surfaces. So stepping up one level and then toggling back and forth a couple times, we can see that a lot of these patterns are consistent from one depth slice to the other. These can be interpreted. The actual interpretation or point picking is completed directly on the individual aligned seismicity hypocenters, believed to be indicative of injected fluid flow and fluid flow barriers or discontinuities. So should mention that during this phase, a lot of times it's good to vary the display parameters to emphasize certain alignments. And the comment to be made next is that we're going to step to a smaller area for viewing within the next slide within the blue dashed lines. Here, we're going to look at a depth slice from 7,000 to 7,500 feet subsea in the North Geysers, and introducing these seismicity hypocenter picks for the aligned hypocenters that have been determined by multiple depth slices. The comment to be made on this would be that apparent steam reservoir compartmentalization is more evident within certain depth intervals. This is very easily seen on this view. And now we're going to step into an even smaller area within the blue dashed line and look at it on the next slide. In this case, the interpreted faults and fracture surfaces have varying degrees of importance for 3D structural model development and well planning. The selected surfaces appear to define zones of significant reservoir compartmentalization. Now, I've highlighted the Pratty 14 well, which we discussed on the next slide, and make some comments on the correlation of a high permeability zone determined during drilling and an interpreted fault zone. So we've seen a direct correlation between 2020 fracture and fault surface interpretation based on these historical seismicity patterns and a 1987 high permeability zone based on the Pratty 14 drilling program. Stepping in just a bit to look at this well in more detail with this intersecting fracture, we then look at the summary geological log for this well, and stepping in here and viewing this in more detail, the comments can be made that the fracture zone, which is extensive in this well at the intersection point, is identified by steam entries in red arrows, the water entries as bold blue arrows, and lost circulation zones as more pale blue arrows. And also, increased rate of penetration is shown on the drilling log, indicated by the black arrows at right. And this is indicative of drilling within a fracture zone. Another important thing is that large euhedral quartz crystals occur, which are indicative of drilling into open fractures. There are over 375 fault and fracture surfaces now available within the Geysers structural model. These are picked directly on the line seismicity hypocenters, and they're picked using variously oriented seismic slices. They're continually refined during the well planning programs, which occur continuously. In the Northwest Geysers, primarily there are near vertical faults, and the orientations are consistent with the regional stress field. And in the Southeast Geysers, there are more non-vertical faults, and these radiate from the shallowest penetration of the granitic intrusion or felsite. Now I'd like to show a structural boundary interpretation based on a seismicity slice, a cross-sectional one from 1984 to the present at a 4-year interval. We will do an animation. So this seismicity slice that I will show is seen in the map view on the left, 1,000 feet wide, and we're going to view it from the west, and that will be seen in the image at right as we animate through, and also show the cumulative water injection along with the seismicity. So as I progress through this animation, we can see the water being introduced in map view, and we can also see the seismicity illuminating the subsurface down to a depth of nearly 15,000 feet subsea. The top felsite is seen at right as black diamonds, and at left as a color scaled surface. Now, importantly, the surface interpretation or the mapped surface faults for what's been designated as the magnitude 4 divide are shown and are very well correlated with the subsurface representation of this as a seismically illuminated fracture zone. Stepping forward, I'd like to show this correlation of mapped surface faults and the subsurface fault and fracture interpretation for these two zones, the magnitude 4 divide and the ridgeline fault zone. So first of all, I would like to note that the steam reservoir is displayed here as color scale depth contours, and the ridgeline fault zone and the magnitude 4 divide fault zone are shown as the black lines on this image. These are the surface geologic mapping. And now from the subsurface interpretation of the seismicity alignment, steam entries, and lithology logs, we can see these surfaces, and you can see how well they correlate with the surface information. And some of these are more steeply dipping than others, but they all intersect the surface at the location of the mapped events. And one comment to make, the magnitude 4 divide fault zone has an unusual name. Northwest of this major structural boundary, seismicity extends significantly deeper, and here exists 35 of 39 seismic events greater than magnitude 4. Now I'd like to show a structural model analysis within the volume slicer. So first of all, the comment to be made is that the cumulative water injections and seismicity hypercenters will progress from 1984 to the present in this animation. So first it will turn to a cross-sectional view, and I would like to note that the listings at right show the objects included within the view. So the seismicity continues to be introduced into this structural model through time, along with microseismic stimulated reservoir volumes. You can see 4 of them now within there, and the surfaces that have been constructed using the structural and stratigraphic modeling workflow were also included. An additional video will be shown, and this one is showing the use of the volume slicer to limit the 3D structural model to a target area for analysis when the southeast geysers. So we push the walls of this slicer in from the southeast, from the southwest, and then from the northwest, and limit the volume to this specific, specifically as shown in this view. And then stepping on to the next slide, we can see this southeast geysers volume, and the comments to be made here are near Anderson Springs. Induced seismicity exists primarily within the uppermost granitic intrusion or fell site. The stimulated depth descends toward the east. And now rotating that around a bit and looking at the same fault in yellow on here as in the map view at left, the seismicity suggests water injection from the south-southwest is being inhibited along this yellow interpreted fracture surface and significantly more vertically extensive to the southwest. There's high seismic event density from about 4,000 to 12,000 feet subsea. So that's important in our model construction. Quickly, I'd like to discuss mitigation investigations. In this case, a well by the name of 87G21 was of concern. We're going to look at this in 2 views, from map view and from a cross-sectional view from the east-southeast. The same interpreted fracture is shown in both of these. And once again, the cumulative water injection volumes are equivalent to a disk radius, in this case black, for better emphasizing. As we step through this, the important thing to note is that there is a very preferential distribution of seismicity to the southwest side of the interpreted fracture. And stepping up to the present day, the comment to be made is that reservoir compartmentalization can introduce significant thermal and pressure variations into a limited reservoir volume, and understanding compartmentalization can assist with induced seismicity mitigation at the geysers. Another tool to be used is the Emerson SKUA microseismic stimulated reservoir volume analysis tool. The parameters are set up within the window at left. The center left view shows the analysis volume from above, and the cell sizes are determined based on the needs of the analysis. And in the view at the lower right, we can see this isolated volume from a distance and cross-sectional view. And I'll rotate this around, and the important thing to see here is that the stimulated reservoir volume is not uniform throughout the analysis volume, but is actually has a very distinct pattern. And a final comment to be made on this is that the volume of stimulated reservoir can be seen throughout time by comparing these introduced stimulated cells over time. Now let's quickly discuss improved water distribution for potential seismicity mitigation at the geysers. The well 87G21 discussed previously was primarily responsible for magnitude 3 and greater seismicity in the Calcasieu power plant area. So a 5-well program was developed with our central operations drilling and resource management staff. We established guidelines for improving the water injection distribution for the wells shown, and importantly, the seismic results since these modifications are very encouraging. And a final interpretive view, I'd like to discuss the 3D pre-drilling analysis within the field-wide structural model. Southwest boundary of a structural model defined by the Big Sulphur Creek fault zone is discussed here. The important thing being that the Big Sulphur Creek fault zone, as defined in surface mapping, is shown by the black line from northwest to southeast. And the subsurface interpretation is, and I'm flipping it on and off, is the yellow surface or series of yellow surfaces that occur there. And the comment to be made is that fluid flow appears to be inhibited to the southwest by fracture surfaces associated with the Big Sulphur Creek fault zone. So either the fracture surface itself or changes in permeability from one side to the other responsible for that. But in any case, there is a change in fluid flow ability in certain zones of the field. Now, I'd like to talk about a northeast boundary of this structural model defined by the Big Sulphur Creek fault zone. There's a splay fault coming off of the main fault that seems to be responsible for also inhibiting fluid flow. So fluid flow appears to be inhibited to the northeast by a fracture and fault splay associated with the Big Sulphur Creek fault zone. So this was all important information used in one of our well pre-drilling programs to determine where to target a new well. And one thing I'd like to show now is the seismicity and introduce a couple of years of seismicity for 2020 and 2021 that are shown as black symbols that are twice as large as the others. And these indicate a new reservoir recharge volume from a well we call GDC 34, which has recently began receiving water injection. So the important comment to make here is that we see this distinct compartment and we see new water injection adjacent to that doesn't seem to be interfering with that original compartmentalization. A comment to be made here is that lateral separation of multiple existing water injection and steam production points is assisted with well planning, has assisted with well planning, and this is determined using a combination of SKUA GoCAD tools. Those are listed here. And what we're seeing in these views are a lateral separation from adjacent water injection entry points and from adjacent steam entries where steam is recovered. This is all important to know when we're targeting a new well because we have so many wells at the geysers and they are all directionally drilled. Finally, the utilization of the geysers field-wide structural model. A refined understanding of the geysers fluid flow paths, fluid boundaries, reservoir heterogeneity, and reservoir compartmentalization assists with well planning and targeting, real-time drilling analysis, reservoir management, and also provides the potential for improved seismicity mitigation. This 3D structural model visualization is also a very valuable tool for public outreach concerning induced seismicity at the geysers. And I'd like to finish up by pointing out that, as mentioned at the beginning, there are many experts in a range of specialties that contributed information that was used in this project. And I won't read through all this, but I wanted to leave it on the screen for a moment to acknowledge these people.